This video is about the vapor pressure of pure liquids. So what I have pictured here is a scene that we might be familiar with, right? So we've just had a rainstorm, and now there are puddles all over the courts here. So what we notice is that after some time, some of these areas begin to dry out. The water appears to go away. Now, this is really normal, right? We call it evaporation. But if you think about on this particular day, maybe it's not all that warm outside. Maybe the temperature is a nice, comfortable 20 degrees Celsius. And so we wonder, well, why is this water going away? We're well below the boiling point of water, 100 degrees Celsius, which is the temperature at which water converts into a gas. So why is it that water molecules are leaving the liquid phase and converting into gas? Because to do that, don't we have to boil the liquid? And it certainly isn't boiling out here. So why is it that water is able to evaporate? So to answer that question, we're going to need to think some about intermolecular forces that we've been talking about and to look at this idea of vapor pressure. So let's imagine that we do this experiment. So I have a container, and initially I pumped out all of the air in that container. And then what I do is I fill the bottom part of the container with a liquid. So at the instant that I have just filled it, it might look like this. So the little blue spheres that are here represent in the bottom of the container, represent the molecules, right? And so what we're going to do is a little blow up of, let's say, this region. So I'm just going to make a blow up of this region so we can see what it looks like up close. So this little region, we've got some of these blue molecules. So here they are. And then we've got empty space above them, right? So I won't draw its neighbors in here. We've got empty space up here. So this is vacuum. Pressure is equal to 0 atms. So what we know, why are these molecules not immediately just moving up here? Well, the reason is that they are held together by intermolecular forces. So I'm going to draw some dotted lines in here representing some forces between these particles. So these particles undergo intermolecular forces that hold them together. So that's one thing we should notice about this microscopic picture. The second thing that we should notice is we're at some temperature. So room temperature is typically taken to be 25 degrees Celsius. And what we know about temperature is that temperature is related to average kinetic energy. So I'll abbreviate kinetic energy, KE, and this little fish symbol that I've drawn right here means proportional to. So temperature is related to average kinetic energy. Kinetic energy, you will recall, is energy of motion. So even though I've drawn a snapshot picture here, what we know is that all of these molecules are trying to move around. These connections, these intermolecular forces, are constantly being broken and remade. So some of these molecules are moving slowly in one direction, whereas other molecules might be moving quickly. Okay? Well, since all these directions that they are moving are potentially random, it is possible that one of these molecules has gotten a little kick and is moving upwards into this empty space that's up here. So what might prevent it from going up there? Well, these intermolecular forces act rather like Velcro that attach this molecule to the rest of the molecules. But if it has enough kinetic energy, it can break free. In the same way that if you jump off the ground, you cannot get very far. You're going to be pulled back down to the ground by gravity. But if you were to jump hard enough or had a jetpack or a rocket engine strapped to your back, you might be able to blast off and actually escape Earth's gravity and go into space. So the same thing is happening to here. Here, if the kinetic energy is bigger than the force that holds these molecules together, this molecule can jump up into the gas phase. Now, one other picture I want to remind you of is this graph. So I told you that temperature is related to average kinetic energy. So what we're going to do a plot of here is kinetic energy. Now, in this model that I've shown you, these molecules that are down here in the bottom of my beaker, they all have a kinetic energy that's set by this temperature, but they do not all have that average kinetic energy. Some have a higher kinetic energy, some have a lower kinetic energy. So we can draw what's called a distribution, and so this y-axis I'm going to label percent of molecules. So we want to know the percentage of molecules that have any particular kinetic energy. And the graph might look something like this. So it gets kind of closer and closer to zero as you go this direction. So right here, this would be the most probable kinetic energy, and if the curve isn't exactly symmetric, maybe the average is kind of right over in here. So maybe this is the average kinetic energy, a little bit off the peak here because there's a little bit of higher kinetic energy over here. So this might be the average kinetic energy. So this is a distribution, right? So we've got a few molecules, a small percentage that are moving really slowly, have a small kinetic energy, and a small fraction that's also moving really fast, ripping around with a lot of energy of motion. Most of them are in between. So let's imagine that there is some kinetic energy right here by this dashed line that is like a threshold kinetic energy. If a molecule has this much energy or more, it will have enough energy to break free of its intermolecular forces and escape into the gas phase. So I'm going to shade in this area right here. So underneath this curve, this part that I've shaded in purple right here, all of these molecules have at least enough kinetic energy to escape. So if they happen to be at the surface, that's what they're going to do. So what happens in this diagram as time passes? So time passes. So as time passes, we will have noticed that some of these molecules will have escaped up here into the empty space. So we now have a gas that's above the liquid. So some of these molecules have enough energy to escape the vapor phase, and then they become gas phase molecules up here in this empty space moving around. Now this will continue to happen as time passes. More and more of these molecules will continue to move up here, and until we have emptied out all the molecules that have enough kinetic energy to escape into the vapor phase. But because we're at a constant temperature of 25, we simply add more heat energy in to this. So every time we pull a molecule up, we're breaking intermolecular forces. It takes energy to do that. That's an endothermic process. So we're decreasing the average temperature, right, because we move some molecules. So we have to add heat into this system. Remember that Q right here is our symbol for heat. So heat is coming in from the surroundings to keep this at the same 25 degrees. So eventually it starts to get pretty crowded up here in the gas phase. And at some point there might be one of these molecules that happens to be moving pretty slowly in a downwards direction, so I'll draw a little short arrow. So it's moving pretty slowly. And what's going to happen when it bumps into these molecules that are down here in the liquid phase? Well, these intermolecular forces are going to take hold of it, and it's going to stick there, rather like a ping pong ball coated in Velcro thrown against the other side of the Velcro. It's going to stick, right? So that molecule is going to stick. So at some point we get to this condition where the rate at which molecules are leaving, so that would be the rate of vaporization, and over here molecules are coming back in, and if that's happening at the same rate, the rate of condensation, then we have this interesting condition where nothing is going to appear to change. The number of molecules that are in the liquid will stay the same because we're adding one for every one we take away. Similarly, the number of molecules that are in the vapor phase will stay the same because we're adding one, again, for every one we take away. So that's a very important condition that is known as dynamic equilibrium. So equilibrium is sort of a word that we use to saying that there's no net change. And this word dynamic just means always in motion, because in this picture there are always molecules leaving the liquid phase and there are always molecules coming back. So we reach this condition of dynamic equilibrium when the rate of vaporization, I'll just say rate of VAP, is equal to the rate of condensation. I'll just write COND as my abbreviation there. Okay, so when those rates are equal, we are in this condition of dynamic equilibrium, and there's going to be no net change. Now let's go back and think about what's going on in this gas phase. So in this gas phase, we've got some molecules in here now, and we know from our study of gases that pressure is equal to the number of moles of gas times this gas constant R times the temperature T divided by the volume. So this space right here has a particular volume. We're at a temperature of 25 degrees Celsius, and now we've got some moles of gas up here. So the important thing about this comment is that inside this space we now have a pressure that is greater than zero. Remember, we started out at a pressure of 0 atms up there in that empty space, but now we've got some gas molecules up there, so we've got a pressure, and the pressure is going to be greater than 0. So we call that the vapor pressure of the liquid. So let's write a little definition of that down here. So here's a definition. Vapor pressure is the pressure of a gas that is in equilibrium with its liquid. So what we've just pictured up there. So you might remember that I talked about evaporation earlier, and how does that happen? Even though we're not at the boiling point. So here, if this liquid is water that we've been looking at in our container right here, we know we're at 25 degrees Celsius, which is not at the boiling point, but certainly some of these molecules have enough kinetic energy to escape and go up here into this vapor phase. So up here in this vapor phase, we'll have some molecules. And so those molecules are leaving. What's going on with evaporation, like up here in this picture, is that I don't have a closed container. I don't have a box that's keeping these water molecules as they escape staying in this box. So these water molecules, as they escape, do not have to stay in this box. So some of these water molecules that have enough kinetic energy to escape into the vapor phase, they're going to come out here and never be heard of again. So away they go. Bye-bye, molecule. And so the water molecule leaves the scene completely. And so eventually these water molecules will all leave the scene, as long as we're not in complete equilibrium with the vapor out here. And if we are, it will be really foggy or in fact raining, because when we get to that point, water will condense out of the air and rain back into the ground. So as long as it's a little bit drier than that, these water molecules will likely leave completely. So that's how evaporation works. It's just this process. Some of the molecules at the surface of the liquid have enough kinetic energy to break free of their neighbors and go into the vapor phase. If it's a closed container, then that creates a little bit of pressure that we call the vapor pressure. Now there are a couple of interesting points about this. So first off, we can imagine that we've got a different kind of container here. So we've got our liquid here back down in the bottom, and now we've got a container with a movable wall. So I can push down on this movable wall with a certain amount of pressure. So we're going to call that P sub EX for external. Okay. Now these little molecules are going to be leaving the liquid phase down here. So there's some molecules leaving the liquid phase. That's supposed to be an arrow going up there at the same rate that molecules are going back into the liquid phase. So molecules are leaving and entering the liquid phase. So we build up a certain amount of pressure inside this container. So if the pressure inside here, if the vapor pressure, so I'll call that P sub VP, is equal to the external pressure that I'm applying, then it means that gas is stable in this system. Otherwise, we're pushing these molecules back in. And so little gas bubbles that might form inside here, they would get crushed by this external pressure. But little gas bubbles can form inside here, so this is supposed to be not a molecule but a bubble filled with gas. So if the vapor pressure inside this bubble is equal to the external pressure, then the bubble will not collapse. And we know what happens when you see bubbles forming in the bottom of a liquid, right? It's boiling, right? So this is the definition then of boiling. Boiling happens when this condition is met. So when the vapor pressure of the liquid equals the external pressure. Now there's one special external pressure, and that's standard pressure of 1 atmosphere. That's the pressure that we normally experience at sea level here on Earth. And so we call the boiling point at that pressure the normal boiling point. I'll abbreviate boiling point BP. So whatever temperature occurs when you can get the vapor pressure equal to that normal boiling point. Okay, so let's draw a little picture here and think about how vapor pressure, P sub VP, might change as we change the temperature. So if we change the temperature of our container, let's go back up and look at our distribution. So what's going to happen to our distribution at a hotter temperature? Well, if we increase the temperature, we're going to increase the kinetic energy of all the molecules, and we're going to shift everything out this direction. So we just smoosh our curve over to this side. Now if we look at our threshold, we've got way more molecules that have enough energy to escape into the vapor phase. And so that's going to mean that up here in the vapor phase, we're going to have many more molecules than we did before. And we see from the ideal gas equation that if we have more molecules in, that is going to make pressure bigger. So if we think about the connection between vapor pressure and temperature, we might expect to get an increase. So as temperature goes up, we've got more molecules, that's going to increase the pressure. And in fact, it kind of has a curved shape, so it's not linear, but it looks kind of like this. So this is called a vapor pressure curve. And so if we look at a particular pressure, say 1 atmosphere, we draw a little horizontal line over where this intersects our vapor pressure curve. At this point, we will have met the condition where vapor pressure equals an external pressure, PATM, of 1 atmosphere. And at that temperature, liquid will boil at that pressure. So we can drop a little line down here, and this right here is the normal boiling point temperature. So I'll abbreviate that NBP for normal boiling point. So the temperature on this vapor pressure curve at 1 atmosphere is the temperature at which a liquid will boil. So let's think about how vapor pressure and intermolecular forces might be related. This graph shows the vapor pressure curves for a number of different substances. So over here on this axis, this is the vapor pressure in millimeters of mercury. And just as a reminder of some conversion factor, we know that 1 ATM, 1 atmosphere, is 760 millimeters of mercury. And that's the same as a torr, 760 torr. All right, so right up here then, this little line right here is our 1 atmosphere line that goes across there. So all of these vertical lines that go down, these indicate the normal boiling points of these different substances. So we've got some different substances here. The orange line is diethyl ether, then we've got bromine, then we've got ethanol. The blue line is our friend water, so we'll highlight that one because that's an important one. And then we've got octane here. That's maybe a model for what's in gasoline. And then ethylene glycol, which is commonly used as an antifreeze. So here's ethylene glycol up here that boils at just under 200 degrees Celsius. Water, of course, boils at 100 degrees Celsius. So there we go. So these are the vapor pressure curves. And you see that if water is at a lower temperature, say 25 degrees Celsius, then it's going to have a much lower vapor pressure. So if we look down here, maybe 75 torr or so would be the vapor pressure here of water at say 25 degrees Celsius. So maybe it's even lower than that. So somewhere in there. Okay. So that's how these curves work. Now let's think about why is it that these different substances have these different shaped curves? Well, it actually has a lot to do with intermolecular forces. So if we think about it, here's our container again. And we've got our molecules in the container. Draw some molecules down here. And they're trying to leave the liquid phase. So to do that, they have to break all of these intermolecular forces between their neighbors. Right? And if those intermolecular forces are really strong, it's going to take a lot of energy to do that. So in order to get that much energy, they're going to need a really high kinetic energy. And remember, temperature is related to average kinetic energy. So they're not going to have enough energy on average to break free unless the temperature is very high. So that's why these different substances have different boiling points. So these different boiling points, these different vapor pressure curves are telling you something about the strength of the intermolecular forces. So on this list, these would be our weakest intermolecular forces, and down here, ethylene glycol, these would be our strongest intermolecular forces. Now let's see if we can rationalize some of these trends. So if we look at the difference between ethanol and water, water has a higher boiling point, stronger intermolecular forces. So with a water molecule, we have the ability to make hydrogen bonds, which are pretty strong, right? And we can make hydrogen bonds off of each hydrogen, and we can also make hydrogen bonds to each oxygen atom. So there are 4 places where hydrogen bond interactions could occur on a water molecule. If we look at ethanol, ethanol has this hydrocarbon chain, CH3, CH2, and then we have our OH right here. So again, we can make a hydrogen bond to that hydrogen. We could probably make a hydrogen bond to these two oxygens. But over here we can't make a third hydrogen bond, and these interactions here with this little chain, these are going to be, this is a non-polar chain over here, so these interactions are just going to be through dispersion forces. So it is true that this molecule, ethanol, has greater dispersion forces, stronger ones than water, because it's a bigger molecule and a longer molecule, but water, with its ability to form more hydrogen bonds, ekes it out a little bit and is a little bit stronger. So water is going to have stronger intermolecular forces. If we look here at bromine, bromine's a pretty heavy molecule, so heavier than the other two, but bromine is just the same atoms, so there's no electronegativity difference between the bromine atoms, so it has to be a nonpolar molecule. So there's a nonpolar covalent bond between the two bromine atoms, right? So this bond right here would be a nonpolar covalent bond because there is no electronegativity difference between these two bromine atoms. So the trends that we see in vapor pressure are supported by thinking about ideas of intermolecular forces. The stronger the intermolecular forces, the lower the vapor pressure is going to be at any particular temperature. So here if we look at 100 degrees and we go up, we see that the vapor pressure of water is lower than the vapor pressure of ethanol, but the vapor pressure of octane and ethylene glycol are lower still at a temperature of 100 degrees Celsius. So vapor pressure, there's the idea of what it is and how it connects to intermolecular forces.